And probability is a function of events. And events is something about the experiment. That's why I want to start with an experiment. An experiment is a procedure that is carried out under controlled conditions, and it will be executed to discover a null result. A trial is a single performance of an experiment, and an outcome is the result of a trial. So basically, if you flip a coin 10 times, then you have one experiment with 10 trials, and in each trial you may get a head or a tail. A head or a tail is simply an outcome of the trial. Okay. And if you flip a coin, you cannot predict the outcome of the result of the right. You cannot predict the outcome. It means that you can predict cannot predict the outcome. Then you call it a random experiment. All right. So if you flip a coin, or you roll a die, or you roll 2 dice, then you cannot predict the outcomes. That's why you call them random experiment. If you can predict the outcome, you can be sure about that, then you call it a deterministic experiment. Okay. For example, if you drop a rock, then it will fall down, right? So you will be sure about the experiment. If you do it just to confirm something, then that is for sure that is predictable, and it is called a deterministic experiment. All right, or predictable experiment. Now, we knew that we have the concept of experiment. Now we are ready to talk about the sample space. The sample space of an experiment is the set of all possible outcomes, and basically you can there are a lot of outcomes of an experiment, and then the set of all the possible outcomes is called the sample space of that experiment. For example, when you flip a coin, they can get a head or a tail. Then the set of head tail is called the sample space of that experiment. Or you roll a die, you can get the set of 6 values, 1, 2, 3, 4, 5, 6, and then you can then that set is again the sample space. Or you roll 2 dice, you can get it. Now, how about the times of sample spaces? If you can count the elements there in the sample spaces, you call them discrete sample spaces. It means that if a sample space consists of a finite or countable infinite set of outcomes, you call it a discrete sample space. It can otherwise, if it contains an interval of real numbers, then the sample space is called a continuous sample space. Okay, so there are two kinds of sample spaces that you want to learn. All right, now all subsets of a sample space are called events. So you are given a sample space, which is a set of all possible outcomes, and you consider all the subsets of those of the sample space, which means that a subset is a set of some, not all, just some possible outcomes. A subset is just a set of some possible outcomes, and that set is called an event. Okay. Okay, for now, for example, consider the recycle time of a flash. Then when you measure the recycle time of a flash, you can get all positive real numbers, right? Then the set of all positive real numbers is called the sample space of this experiment. And you can come up with some events. Event A1 is the interval from 1 to infinity. That is an event because it is a subset of the sample space. A2, the interval from 1 to 2 is also a subset of the sample space, and it is also an event. Events are a subset of the sample spaces, and they contain some possible outcomes, right? Well, in reality, in practice, you don't really get a subset, okay? Instead, you get sentences, clauses, or statements, claims, right? For example, regarding the first event A1, you can say that it is the event that the recycle time of a flash is greater than 1 second. Okay, suppose that the unit here is second. And A2 is the event that the recycle time of a flash is between 1 and 2 seconds. That makes sense to you? Is that clear? So in reality, you can think of a clause or a statement or sentence for an event. All right. So you can have many events, right? You can have many events. And how can you combine events? If you want to combine events, you want to combine clauses. All right, you want to combine clauses. How can you combine clauses in English? In English, if you want to combine clauses, you can use conjunctions or you can use conditional clauses, right? Conditional clauses will be interpreted into conditional clause, conditional probability. For the conjunction, we will have operators. All right. So I want to start. I want to continue with the next part, conjunction or operators. Suppose that we have conjunction and or but. For example, A is the event that you pass the course, this course. B is the event that you pass the course of linear algebra. Then A and B is the event that you pass both courses. A or B is the event that you pass this course, but you don't pass the other course. All right. A but B is the event that you pass this course, but you don't pass the other one, right? And you can use the some operators to denote those conjunctions in probability or in math. You use the product A B to denote A and B. All right. And A plus B to denote A or B. A minus B to denote A but B. Okay. And from the point of view of set theory, you can consider A and B as the product as an intersection of two events, so to subset A and B. A plus B is the union of two subset A plus B. A minus B is the difference, A without B, right, of the two subset A and B. All right. For the last operators, A bar, that give you the complement of an event. For example, if A is the event that you pass this course, then A bar is the event that you don't pass the course. All right. Okay. Is that all clear? Okay. And what we are going to do in this course today, in the meeting today, is to find the probability of A bar, the probability of AB, and the probability of A plus B. All right. There are many operators. There are many properties that you can get for operators, and but now I want to focus only on this De Morgan's rule. It says that the complement of the sum is equal to the product of the two complements. And similarly, the complement of a product is equal to the sum of two complements. All right. So you can see that the complement can transform a sum into a product, and vice versa. It can transform a product into a sum. Okay. In order to prove it, I'm going to draw the diagram. Let's say this is omega, the whole sample space, and you can divide it into two parts, A and B and A bar. You can also divide it into two parts, with this is B and B bar, and then the intersection of AB gives you AB. The intersection of A B bar, you get A B bar. The intersection of A bar B, and the intersection of A bar B bar. All right, now you want to find the complement of the sum A plus B. This is A, this is B. So the complement, then A plus B give you three parts here, and the complement of the union will be the last one. Okay, so it's quite obvious that the complement of the sum A plus B is equal to A bar B bar, right? You can use similar arguments to prove that the complement of AB is equal to A bar plus B bar, right? This is A bar, this is B bar, and the complement of that one is simply AB, right? And then you can get the answer. And please keep that in mind. That would be quite useful for you to work on the probability later. Now I want to provide you some a brief introduction of some types of probabilities. This is the first one. Here are some kinds of probability. The first one is subjective probability, which is a degree of belief derived from an individual's personal judgment or experience about whether a specific outcome is likely to occur. Because it is just a personal judgment, so it's quite biased. All right, it's biased. For example, when I say you have only 50% chance that you can pass the course, you may disagree and you say, okay, you have 80% chance to pass the course, right? Then those values, 50% and 80%, are just our judgments, right? And they are based on our experience. Okay, so they are quite biased. All right. And then you want to come up with something unbiased. You can talk about the relative frequency probability, which is based on how often an event occurs over a very large sample space. For example, when you if you flip a coin many times, right? Let's say you flip it 1,000 times, and then you get 500 heads. Then the chance to get a head in that case is 500 over 1,000, which is 50%. And then you can flip the coin one more time to get a head, and the chance to get a head at that time is 501 divided by 1,001, right? If you keep doing that, then you can update the information. There are two disadvantages here. The first is that you don't have a constant. You don't have a fixed value for the probability, because every time you repeat the experiment, you will get a new value for the probability. Second, and more important, you have to repeat the experiment many times to be able to get the chance. It means that you cannot predict, you cannot estimate it in advance. Just like you want to estimate the chance that your favorite team will win the upcoming game. It doesn't make sense for you to ask your favorite team to play the game many times for you to estimate that probability, right? So this is not really practical. Then you can come up with another one, probability with equally likely outcomes. For example, whenever a sample space consists of n possible outcomes that are equally likely, the probability of each outcome is 1 over n. It is 1 over n, then it seems fair. It seems fair. Just like you roll a die, then the chance to get one number is 1 over 6 because you have 6 options. But you really need this assumption. They must have equally likely chance to occur. However, that is not really practical in reality. Just think about the example of flipping 2 coins, and you count the number of heads. Then you have 3 options, right? You can get no head, exactly 1 head, and 2 heads. What is the chance to get exactly 2 heads? Do you think that the chance is 1/3 because you have 3 options? Not really, right? The chance is actually 1 over 4. The reason is that you have 3 options, but they don't have the same chance to occur. All right, and you see that it is just a very simple example. In reality, it is much more complicated and much more we don't have this assumption, all right, most of the time. Therefore, this approach is not really practical. Okay. Then we are ready to move to a more useful, more general definition for probability. This is not really a formal definition. It just gives you some idea about that. I think that is much more enough for you. You're not mathematicians, so I'm not going to spend time on giving you a formal definition. So basically, probability is just a function of an event. And when you want to say probability, you want to find the probability of an event. That's it. Okay. Probability of an event must be a value between 0 and 1. For any event, that probability has to be greater than or equal to 0. For the sample space, it must be 1. Okay, the sample space is the one that gives you the probability 1. For 2 disjoint events, A and B, which means that they don't occur at the same time, the probability of the sum A plus B is equal to probability of A plus the probability of B. Okay, we admit it. We take it for granted. All right. And for example, suppose that A is the event that you pass this course, and B is the event that you fail the course. Then the probability that you pass the course or you fail the course is equal to probability that you pass the course plus the probability that you fail the course. Do you understand? Okay. Here are some properties of probability. First of all, the probability of the complement is 1 minus the probability of A. For example, A is the event that you pass this course, and suppose that that probability is 70%. And what is the probability that you don't pass the course? The probability that you don't pass the course is the probability of A bar, which is 1 minus the probability of A, which is 70%, so you get 30%. All right. If, as I said, if A and B are disjoint, then you get the probability of A plus B is equal to probability of A plus the probability of B. In general, if you have many disjoint events, okay, let's say A1, A2, AN, then the probability of A1 plus A2 plus A3 and so on should be equal to probability of A1 plus the probability of A2 plus the probability of A3 and so on. Okay, if they are disjoint. All right. Okay. Let's consider the following example. If three falcons are tossed, what is the probability that three faces will not be the same? What do you think? Okay, let's see. 7/8. 7/8 is that for? Okay. Are you talking about the first problem, right? How about this problem? Suppose that A is the event that three faces will not be the same. Then you want to find the probability of A, and because of the word not, I would use the complement for that. So you get 1 minus the probability of A bar, and then you come up with what is that? The probability of A bar is the probability that the three faces are the same, and you get 6/36. Why? Because you can, if they are the same, then you can get. I'm sorry. The over 36. I think it should be. What is that? 2 over to the third. Because you flip 3 cons, so there are only 2 cases, right? There are only two cases with 3 heads or 3 tails, and then you come up with 3 over 4. Make sense? Is that clear? All right, 75%. That is for the first problem. The second problem, question 3. In this problem, we want to find the probability that in a set of 10 people find the probability that at least one pair of them will have the same birthday. And for convenience, we assume that there are only 365 days a year. And you want to find that probability. So the probability you want to find is simply the probability of A, where A is the event that at least one pair of them will have the same birthday. That is A. And you want to find the probability of A. And that would be 1 minus the probability of A bar again. What is A bar? Do you know that? A bar is the event that they don't have the same birthday, right? You cannot find any pair of them having the same birthday. It means that they have different birthday. Okay, and because they have different birthday, then you can come up with the following values, value for the probability. If you don't, because there are 10 people, you don't care about them, don't care about their birthday, then it just you don't care if they are the same or not. So you have 365 for the first person, 365 for the second person, and so on, right? But if you want them to be different, their birthdays to be different, then the first person has 365 options to choose his birthday, right? 365. And then for the second person, you want that person to have not to have the same birthday as that of the first person. So the second person has only 364 options. All right, and you get up to 356. Then this expression will give you the desired probability. Is that clear? Okay, that makes sense.
Teacher, can you explain the question 3 in Vietnamese?
Question 3.
Yes, I still don't understand the numbers.
Okay, I see. As you may see it, well, what is A bar? A bar is the event that that you cannot find any pair of them which having the same birthday, right? You cannot find any pair. You cannot find 2 people with the same birthday. Am I right? You cannot find any two people who have the same birthday. Am I right? So A bar is the events that they have different birthday, correct? So the first person has 365 options to choose for the birthday. right? And the second person, for the second person, because that person shouldn't have the same, because the second person shouldn't have the same birthday, right? Without the with the first person, so that would be 364 options, and you get 364, and the same for the other. So you get 364, 365, and now you get 356, right? Is that clear?
Yes, it's clear to me now.
Okay.
Thank you, teacher.
Yeah. Oh, yeah. So in this case, you need to talk about for convenience. You have the case 365. Now, if you want to talk about the other options with 366 day per year, then you have to consider you need to consider the diagram, like the chance for those who with this with a another option, right, on that day. I think on February the 29th. Then yes, we need to consider one more thing to do it, one more case, in fact. But I will skip that part. All right, you can try that one, and please, and you can tell me the answer, and we can discuss next time. All right. Um, that would be doable. You may want to try it at home. All right, and tell me what you can get. All right, now I want to consider the case. I want to revisit the rule probability of A plus B equals the probability of A plus the probability of B. If they are disjoint, so the intersection is the empty set. What if they are not disjoint? If they are not disjoint, then you come up with probability of A. You come up with this one. This is A. This is B. Okay. And then you come up with probability of A plus B, and you get probability of A. You expect to get probability of A, probability of B. You get that one for A. You get this one for B. All right. Okay. And you see that you count the intersection of A, B 2 times, right? So I'm going to cross that part, and that's why we have one more terms minus the joint probability of AB. Okay. That makes sense? And you call this formula the addition rule. Is that clear? You can also generalize the idea for more events, for 3 events or more events, like this one. Okay, so you can see that you can have the sum probability of the sum of for 2 events, and again, if they are disjoint, then the intersection is the empty set, and then you can eliminate the last term. If there are 3 events, you get probability of A plus the probability of B plus the probability of C minus the jump probability of 2 events plus the probability of 3 events, the jump probability of 3 events, and so on. if you have more events, then you can have the plus, the minus, and then plus, and something like that. So you see that the signs are alternating, right? You have the sum of all the probabilities of a single events, and then minus the joint probability of two events, and then plus the joint probability of three events, and so on. Okay. Let's consider the following example. Okay, many of you got 10%. I think that is the correct answer. Suppose that V is the event that the patient has a viral infection, and B is the event that the patient has a bacterial infection. Then the event that you want to deal with is VV, right? The patient has both infections. And then you can use the deletion rule to get B plus V is equals to probability of B plus the probability of V minus the probability of BV. This is 0.7, right? This is 0.4, and this probability is what you are looking for. Now you want to find the probability of the sum B plus V, and that is 1%. Why? Because the doctor decides that the patient has either a bacterial infection or a viral infection or both. So it must be 100%. Okay, that's why you can solve for the joint probability BV, and you get 10%. Do you understand? Okay, is that clear? Is that all right?
Yeah, teachers.
Okay. let's try this example. You get that? Well, I will denote by U the events that it is related to unsafe conditions. I will denote by C the events that it is unrelated to conditions. I will denote by D the events that it is in day shift, and S for swing shift, and N for night shift. Then I want to find the probability that uh, it was attributed to unsafe conditions. So you want to find the probability of U, and use some odd numbers here, right, to get 23%. This is going to be 77%. This is 45%. This is 28%. Then you come up with 27%. Okay. Then the probability of U is 23%. Correct? For the second problem, you want to find the probability that it did not occur on the day shift, so D bar. And you use the probability of the complement 1 minus the probability of D. The probability of D is 45%, and this is 0.55. Understand? For the last question, you want to find the probability that it was related to unsafe conditions or night shift. So you get this. And you have the addition rule, the probability of U plus the probability of N minus the joint probability of UN. And you come up with, for the probability of U, you get 23%. For the probability of N, you get 27%. And for the last term, you get 5%. So altogether, you get 0.45. Do you understand? Okay. All right. Okay, let's have a break. Or maybe perhaps I can go for further a little bit, and then we can have a break later. If that's fine. Do you want to have a break now, or you want me to go keep moving, keep so that we can have a break later, a little bit later. If that's fine.
I think we should continue.
Pardon me. Can you speak a little bit louder?
I
Hello.
think we should continue.
Okay, that's fine. Then we can move on with the. I think we are ready to move on to the next part of conditional probability. So let's say let's go back to this example. The probability of U is 23%. All right. In this case, you don't know any information about the shift, right? If you do know that, if you know that it is in night shift, then what is the probability that it is related to an unsafe condition? How about that? Should it be the same as 0.23? Not really, right? Another example, suppose that based on the past experience, I know that the probability that a person can pass the course is 70%. What is the probability that the student can pass the course if his midterm score is 10? What do you think? Do you think that it is still 70%, greater than 70%, or less than 70%? What do you think? Yes, I think so. Greater than 70%. So the probability that a student can pass the course is not a fixed value, right? It depends on the information. It depends on the information you get. If you have no information, it is 70%. If you have some information, then it is something different. Okay, and you want to find a ways to define that probability. You call this one conditional probability. All right, just like if M0 happens, okay, if this one occurs, what is the probability of A? That is what you want to study. Okay, and this one is called conditional probability. All right, just like you have conditional clauses. Am I right? Okay, so this is what we want to do. Oh, back to the problem. Back to this problem. One student asked me about this. He wants to ask about the value of the jump probability UN. You see that this is U, right? And this is N. So you see, basically, you can see that this is the value that you want to use, right? 5%. That's why it is 5%. Is that clear? All right. Okay. Is that okay? Zoom is that fine? All right. Okay, back to the definition of the conditional probability. How can we define it? Well, I want to start with the unconditional probability. Just like you have A. Okay. Let's say suppose that you have a square like this one. All right. And then you consider this one, right? You divide into two equal parts like that. And this is this. Let's say this is, I don't know, this one by A. This is A. Okay. And the side R1. What is the probability of A? Can you tell me? The probability of A in this case is 1/2, right? This is the area of this one. Am I right? If I if I consider another one like this, let's say you get this area, this triangle, then what is the probability that if you pick one value, 1 point from the square, what is the probability that it belongs to the triangle? Then again, it is the area of this triangle divided by the area of the whole square, right? And you can check to see that the probability that you can pick a value, a point from the triangle, is basically 1 or 4. Am I right? So you divide the area of the triangle by the area of the whole square. Now back to this problem. Back to this case, you get the whole sample space with one event A like that. Then I can say the probability of A is simply the probability of A over the probability of the whole sample space. Okay. Do you understand? Now the what is the sample space? The sample space is the set of all the possible outcomes. Okay, it is the set of all the possible outcomes. So when you know that B occurs, then B bar never occurs. You can cross that part. Okay. and then you come up with then omega becomes B, right? Omega becomes B, correct? Omega becomes B. The sample space becomes B, right? Because B contains all the possible outcomes. B bar contains the elements which are not possible outcomes. So you should exclude all the elements of B bar from the set of all possible outcomes. That's why the set of all possible outcomes is B, right? Then omega becomes B, and the denominator becomes the probability of B. For A, you get AB, then the numerator becomes the probability of AB. And this is the definition of the conditional probability of A given B. Do you understand? Is that all clear? Is that all clear to you guys?
Can you explain this one again? Sorry, sir.
You want me to talk about that a little bit, like one more time?
Yes.
Okay. Just like, all right, let's say you want to find the probability of A. The probability of A is A over the whole sample space, right? Omega, correct? Right? And if you know that B occurs, then B bar never occurs, correct? If B occurs, then B bar never occurs. Therefore, the set of all possible outcomes becomes B, right? What is the set of all possible outcomes? Omega. Now it is B, not B bar any longer, right? You need to exclude the B bar. So you get B, so omega becomes B. And A becomes AB, right? A becomes AB. Because you just exclude that part. Then you get AB. And this fraction is called the conditional probability of A given B. Do you understand?
Yes, it's okay, teachers. Yeah.
Okay. Then you get the following definition. All right. All right, let's consider the following example. Suppose that there are 10 items, 10 defective items with surface flaws, 18 defective items with without surface flaws, 30 non-defective items with surface flaws, and 342 non-defective items with without surface flaws. So altogether, there are 400 items. If you pick one item randomly, all right, what is the probability that the item is defective? Can you tell me? What is that? The probability that the item is defective is 28 over 400, correct? Am I right? Do you understand, you guys? Is that clear? Okay. And now, if you find something wrong on the surface, let's say you find some surface flaws, what is the probability that it is defective that it is a defective item. That it is a defective item. What is that? Do you think that it is greater than, the same, or less than 28 over 400? It should be greater than, right? If you find some flaws on the surface, then you think that it is not a good one, right? Well, it is. We cannot conclude that for sure, but it is just one indicator that you may get a defective item, right? How can you get this probability? You can use the definition. That is the probability of df over the probability of f. The probability of f is simply 40. Oops. 40 over 400. And the probability of df, what is the probability of df? The probability of df is the df is here 10, so it is 10 over 400. Okay, so you get 10 over 40. Okay, 1/4. So if you find nothing, if you find something wrong with the surface, then the probability that it is a defective item is 1/4. Is 10 over 400. All right, or let's say 100 over 400, right? If you have no information about that, about the surface, then the probability that it is a defective item is only 28 over 400. But if you find some flaws on the surface, then it is 100 over 400. So the chance is about 4 times. All right. That makes sense. You can also get this probability by changing the sample spaces. Let's say you have a look at this. You have f, given f. Given f means that given f means that you want to focus on this column and you ignore the other columns. You can ignore the other columns, and then you can get the value only 10 over 40, right? That's it. So the probability of D is 10 over 40. That's all. That's everything you need to do. Well, this way seem easier to do. However, it is not a good way to do if you have much more events. All right, and you have so many events, and the problems becomes more complicated. So you don't really want to change the sample spaces every time you compute the conditional probability, right? So that's why it is better to use the formulas for that, the definition for that. Okay. Let's consider the following example. Oh, by the way, I want to give you a brief introduction about the product rule first. You get the probability of AB, A given B, is the probability of AB divided by the probability of B. And then you get the probability of AB equals the probability of A of B times the probability of A given B. Okay. And then you can let's consider the following example to illustrate what I just mentioned. A batch of 50 parts contains 10 made by tool 1 and 40 made by tool 2. Select 2 parts randomly. what is the probability that the first part came from 201 and the second part came from 202? Denote by E1 the event that the first part came from 201. In E2, the event that the second part came from 202. All right. Then it is very easy to observe that the probability of E1 is 10 over 50. Okay. The probability of E1 is the probability that the first part came from 201, and that is 10 over 50. The probability of E2 given E1 is the probability that the second part came from 202, given the fact that the first part came from 201. So if you already knew that the first part came from 201, then there are only 49 parts left in the batch with 90 items made by 201 and 40 items made by 202. Then the probability of getting a part which came from 202 is 40 over 49. All right, and then you come up with the two fractions, 10 over 50 and 40 over 49, the two probabilities. And if you want to find the probability that the first part came from 201 and the second part came from 202, then you get 10 over 50 times 40 over 49. All right, and this is the value you get. In this case, you use the formula that the probability of E1, E2 is equal to probability of E1 times the conditional probability of E2 given E1. And that is this formula. And this is the formula that I just proved. All right. The probability of AB equals the probability of B times the conditional probability of A given B. Or the probability of AB equals the probability of A times the conditional probability of B given A. Is that all clear to you? That makes sense? Is that clear? That should be okay, right? May I move on? Okay, good. Let's consider the following example. All right, let me see. You get for question A. The sum is 6, so you get the probability of B. The numbers are not equal. Not equal, so I'm going to use the counterbalance one minus the probability of B bar. B bar is the event that the numbers are equal, and you get 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6, and you get 6 options out of 36 options. So you get 5 over 6, right? For conditional probability of B given A, what do you get? B given A, you should get the John probability BA over the probability of A. The probability of A is the probability that the sum is 6, so you get 1 and 5, 5 and 1, 2 and 4, 4 and 2, 3 and 3. So you get, what is that, 5 over 36, I think, right? 5 options. For BA, you want to get the sum 6 and the numbers are not equal, right? So you get 1, 5, 5, 1, 2, 4, 4, 2, but you have to exclude the case 3 and 3 because they are the same. That's why you get 4 over 36, and the answer is 4 over 5. Okay. If you compare them, you see that the conditional probability of B given A is not the same as the probability of B, and that is right. So we say that A and B are dependent. Is that clear? Is that okay, you guys? For question B, what do you want to do? A is the event that the number on the first line is even. F is the event that the sum is 7. And you want to find the probability of F. F is the event that the sum is 7. The sum is 7, so you can get 1 and 6, 6 and 1, 2, 4, 4, 2, right? So you get 6 over 36, which is 1 over 6. For the conditional probability of F given E, then you come up with the John probability EF over the probability of E. The probability of E is 1/2 because that is the chance that the first die is even. Okay. The first die is even, then you get 1/2, and the probability of EF is the probability that the sum is 7, and the first die is even. So you get 2 and 5, 6, 4 and 3, 6 and 1. So you get 3 over 36. So altogether you get 1 over 6 again. So you can come up with, you see that they are the same, right? And then you can see that the probability of F given E is the same as the probability of F. All right, they are the same, and we can say that E and F are independent. We say that they are independent because knowing that E occurs doesn't change the chance that F occurs, right? If you know nothing about E, the probability of F is 1 over 6. If you know that E occurs, then the probability is still 1 over 6. Unlike the previous case, if you know nothing about A, then the probability of B is 5 over 6. If you know that A occurs, then the probability of B is 4 over 5, right? Is there any question so far? Should be okay for you? That is fine, right?
Yes, sir.
Okay. All right, then we can come up with the definition of independence. We say that A and B are independent if the conditional probability of A given B is equal to probability of A. Okay. So knowing B occurred doesn't impact whether A occurred. You can prove that the following statements are equivalent. A and B are independent if and only if the probability of A given B is equal to probability of A. The probability of B given A is equal to probability of B. And then the joint probability of AB is equal to probability of A times the probability of B. You can verify the last equation very easily. Well, you know that A and B are independent if the conditional probability of A given B is equal to probability of A. And the left-hand side is equal to probability of AB divided by the probability of B. Okay, and then you multiply both sides of this equation by the denominator. You should get that one. So probability of AB equals the probability of A times the probability of B. Okay. That is the concept of independence of two events. How about three events? What if you have three events? If there are three events, if you have three events like A, B, C, then we say that they are pairwise independent if any two of them are independent. For example, A and B are independent, A and C are independent, B and C are independent. All right. If so, you can say that they are pairwise independent. All right. So if A, B C are pairwise independent, then the conditional probability of A given B is equal to probability of A. Conditional probability of B given C is equal to probability of B, and so on. So if you have two events, you can always drop the condition when you compute the conditional probability like this one. Okay. So we get this: A given B equals the probability of A given C equals the probability of A. Now I have a question for you. May I say that the probability of B of A given BC is equal to probability of A given B? And then simply the probability of A only? Or let's say, can I just drop the condition? Can I just drop the BC? If I have the conditions alone, like B or C, I can drop them. Can I drop B, C together like this one? The answer is no. The answer is no. Let me give you, let's consider the following example. Suppose that there are three events, A, B, C, like this one, when you flip two cons, which are fair. A is the event that the first con is ahead. B is the event that the second con is ahead. C is the event that they are the same. Then you want to check whether A, B, and C are pairwise independent or not, right? So you want to check the independence of A and B, A and C, B and C. A and B are independent for sure because they are about two different cons. So they are relevant. It means that A and B are independent. Okay, no doubt about that. How about A and C? For A and C, if you want to check the independence of two events, I want to check this equation, right? So I come up with the probability of A. What is that? The probability that the first con is ahead that is 1/2. The probability that the second and the third are the same, which is C, is 1/2 as well. Why? Because there are 4 options. 2 heads, you have 2 heads, head tail, tail head, and 2 tails. So the probability that they are the same is the probability that you get 2 heads or 2 tails. So that probability would be 2/4, and you get 1/2. How about the probability of AC? The probability of AC is the probability that the first one is a head and they are the same. So you get only one case. If the first one is a head and they are the same, then if the first one is a head and they are the same, then the second one is also a head. Therefore, you have only one case that satisfies the requirement, and you get 1/4. Okay, and this is the same as the probability of A times the probability of C. So you can see that A and C are independent. You can also prove that B and C are independent using similar argument. Okay. However, you cannot drop condition BC when you find the probability of A. Tell me, what is BC? BC is the event that the first and the second are the same, and the second is a head. Therefore, the first is also a head, right? And if the first is also a head, then the probability of A is 100%. On the other hand, the probability of A is only 1/2, right? So they are different. Make sense? It means that you cannot drop condition BC when you find the probability of A. Is that all clear to you? Is that clear? Okay. All right. So in order to guarantee that you can drop the condition BC when you compute the probability of A, you need a stronger probability of the 3 events. That would be the mutual independence. So we said that the 3 events are mutually independent or simply independent, or simply independent if they are pairwise independent, and if the probability of A, B, C is equal to probability of A times the probability of B times the probability of C. If you have this, then they are mutually independent. And if they are mutually independent, then you can prove that the conditional probability of A given BC is equal to probability of A. Okay, so if the events are independent or mutually independent, they are pairwise independent. But the inverse statement is not always true. Understand? Okay. Is that any questions so far? Any questions?
Teacher,
Yes. Do you have a question?
can you explain the previous equation that the probability of A given BC equal to 100%?
Okay. What is BC? BC is the events that the first and the second are the same, right? Correct? C
Yes.
is the events that the first and the second are the same. B is the events that the second is ahead, right? That makes sense?
Yes, yes.
So from here, you can conclude that the first must be ahead. Am I right?
Yes.
So the probability that the first one is ahead is 100%. It is always true.
Oh, I see it. Thank you, sir.
Okay. So if you have no information, it is 50%. But if you know that BC occurs, then A must occur. That's why the probability is 100%. Yes, and you see that they are different. Okay. Any questions? Hello. All right. Now you know that you have the concept of independence of two events, and then for three or more events, you get the pairwise independence of three events, and you also have the mutual independence of three events. Okay. If the two events are dependent, if the two events are dependent, then we have this equation that the probability of AB equals the probability of A times the probability of B. If you have three independent events, ABC, then you get the probability of ABC. That is the probability of A times the probability of B times the probability of C. Okay, so you come up with the three events like this one. If you have n events, then you come up with the probability of A1, A2, An. And that would be the probability of A1 times the probability of A2 times the probability of A3, and so on until the probability of An. Okay, that makes sense? And then you come up with this. You come up with this one. All right. For many independent events, and actually, here we need them to be mutually independent. Okay. Now I want to give you give you a brief discussion about the case of Sally Clark. Sally Clark, a counselor in the UK, was the victim of a miscarriage of justice when she was found guilty in 1999 for the murder of two children. Her first baby, named Christopher, died 11 weeks after his birth in 1996. And then 1 year later, in 1997, her second baby, named Harry, also died after his birth 8 weeks. And then you see, it is a very sad story, and there was an investigation about this case, the death of the two babies, and based on the testimony of a doctor, she was found guilty for the murder of the two children. She appeared against the decision, and that was dismissed in 2000. The second appeal was after the second appeal, she was released in 2003. What happened? Well, actually, in 2001, the Statistical Society issued a press release that summed up the two major flaws in the doctor's argument. Okay, so what is he specified in the case of Sally Clark? Sir Wright Meadow studied medicine in Oxford, and he was a doctor at St. James University Hospital. And he claimed that in a single family, one sudden infant death is a tragedy, 2 is suspicious, and 3 is murder until proved otherwise. She was an expert witness in the case of Sally Clark, among the others. And actually, in the case of Sally Clark, he claimed that the frequency of sudden infant death syndrome in a non-smoking family is about 1/8500. And the chance for 2 children from a family like that suffering a sudden infant death syndrome was 1/8500 square, and that would be 1/73 millions. That number, 1/73 millions, is a very small number. Okay. It is even smaller than the chance that you can win a lottery ticket with a high price. And you don't think that you're gonna get it in your whole life, right? Do you? That's why. Okay, so this number is really small, and then based on that, and among the other arguments, she was found guilty. Okay. However, this is not really correct. Okay, what happened? Well, first of all, A1 and A2, suppose that A1 is the event that the first baby died, A2 is the event that the second baby died. Then you want to find the probability of A1, A2, which is the probability that the 2 baby died after their birth, right? And you get, the doctor claimed that this probability is equal to probability of A1 times the probability of A2. However, this is wrong. Okay, if you want it this way, if you want it this way, then you need to make sure that A1 and A2 to be independent. However, there is strong evidence that the sudden infant death syndrome does have genetic or environmental factors that may correlate within a family. Okay, so you should say that the probability of A1, A2 is equal to probability of A1 times the probability of A2 given A1, where A1 is the events that the first baby died, and A2 is the events that the second baby died. All right, so this is what you get. And the first probability, yes, that is still 1/8500. Okay, but the second probability is not 1/8500 any longer, right? Because it is not, this conditional probability is not the same as the unconditional probability. And based on the experience, they can get the value 1/77. Okay, so the actual value should be 1/8500 times 1/77. That is one thing. Second, well, you need to find the probability that she is guilty given the evidence, not the probability that you observe the evidence given the assumption that she is guilty. All right? Do you understand what I'm saying? These two probabilities, conditional probability, are different. All right? Do you remember what I mentioned before? Right here, you can see that the probability of U given N and the probability of N given U, they are different. You can have a look at all the, in this problem, you can check to see that they are different. And therefore, in this problem, these two probabilities are still different. Okay. For example, if suppose that a DNA sequence occurs in 1 in 10,000 people, does this mean that if a suspect's DNA matches that found at a crime, since the probability that he is guilty is still the same? Not really, right? So you have to be careful with the conditional probabilities. And due to these two flaws in the arguments of the doctor, she was released in 2003. However, she couldn't tolerate the consequence of this case, and then she it seemed that she committed a suicide in her home in 2007. All right. Okay, so this is a very sad story. Okay, and one of the reasons is the misuse of the independent events and the product rule of the probability of the product of two events. Okay, is that all clear to you? That makes sense? May I move on? Is it okay, you guys? Is it all clear?
Yes, sir.
Okay. Okay, now let's, so if remember that if you want to use the formula probability of A1, AB equals the probability of A times the probability of B, you need to make sure that they are independent. Okay, now assume the probability that a wafer contains a large particle of contamination is 1%, and that the wafers are independent. If you analyze 15 wafers, what is the probability that no large particles are found? What do you think? Okay, in this problem, there are 15 wafers. Suppose that E1 is the event that the first wafer contains no large particle of contamination. E2 is the event that the second wafer contains no large particle of contamination, and then E15. And then you want to find the probability of E1, E2, E15. And then you come up with the probability of E1 times the probability of E2 times the probability of E15. Okay. The reason is that they are independent. Okay. What is the probability of E1? The probability of E1 is the probability that the first wafer contains no large particle of contamination. And that will be 1 minus 0.01, because 1% is the probability that you can observe a large particle of contamination, right? Okay. And because there are 15 wafers, then you get the power 15. Okay. That's clear. So this problem is very easy. Now I want to talk about the case when the Brooks rule, when you have dependent events. All right. Okay. Now we get the probability of AB. If they are independent, you get the probability of A times the probability of B, right? If they are not independent, what do you get? You get the probability of A, B equals the probability of A times the probability of B given A. All right. Now, what if you have three events? Let's say the probability of A, B, and C, like this one. If you have A, B, and C, then AB plays the role of A, and C plays the role of B. Okay. Then I'm going to get the following formula. You get the probability of AB times the conditional probability of C given AB. Okay. And then you can apply this formula one more time to get the probability of A times the probability of B given A times the probability of C given AB. All right, so you get this formula, right? And again, this is called the Brooks rule for three events. If there are more events, let's say you have 4 events, the probability of A, B, C, D, so you should get the probability of A times B given A times C given AB times D given A, B, C. Is that clear? Is that clear to you?
Yes, sir.
Okay. So in general, this is what you have. The conditional probability can be written in the generalized multiplication rule like this one, and then you come up with the formula for 3 events like this, and for more events, for n events. Okay. Any questions? If you have no questions, then let's go. Let's move on with the following example. Celine is undecided as to whether to take a French course or a chemistry course. She estimates that her probability of receiving an A grade will be 1/2 in a French course and 2/3 in a chemistry course. If Celine decides to base her decision on the flip of a fair coin, what is the probability that she gets an A in chemistry? What do you think? You asked me a question about A, B, A given B. Which one? Which part? Which one that you are talking about?
So I don't understand what the question asks us about. Are they asked us to find P A B or B A in the condition of B?
Oh, you mean that in the example?
Yeah.
Okay, you tell me. That is the point.
Okay, I'm bad at English.
Okay, so basically here, what you can see is that you want, let's say you get the F is the events that you check the French course, and C is the events that you check the chemistry course, and A is the event that you get an A bar, not getting an A, like that. Okay, the chance that she take a French course is 1/2. The chance that she take a chemistry course is 1/2. If you check a French course, then the probability that she get an A is 1/2, right? In a chemistry course is 2/3. Understand? So 2/3 is the probability that she get an A in get an A if she take a chemistry course. Okay, that is 2/3. The probability of C is 1/2. So the probability that she get an A in a chemistry course is the probability of C times A given C. That will be 1/2 times 2/3, and you get 1/3. That makes sense? Is that clear? Is that clear? Okay. Any questions so far? All right, good. Okay, I think that's enough for today. Let's stop here and see you next time.